Hello everyone, welcome to Module 3, and let's take a look at what you've got to do for this Milestone 2 assignment. I'm excuse me, I'm going to just talk about this particular assignment in this video. Now this video of course will be accompanied by an announcement, and if you're watching this video you probably found the link in the announcement, so you probably already read some of that. But in the announcement, I will address some of the additional things that you will need to do for this during this module, and I'll put some links in there to some additional information. But for this video, I just want to focus on your coding assignment and some of the ancillary things in there. For example, this one sort of came out of the blue. I was looking at this earlier. It's like, oh, by the way, submit a state machine diagram completed using draw.io and exported to PDF format. Well, let's go ahead and take a look at that first, because you know, if you were designing this from top down, you know, you'd probably do this before you actually wrote the code. So let's take a look now. I, of course, was not familiar, I admit, with draw.io, so I looked it up, and you can find Draw.io online at app.diagrams.net. So let's go there, app.diagrams.net, and I made a state machine. So it's you just start with a blank document. I didn't see a template for a finite state machine, but this is what I came up with, and certainly you, oh, let's see, let me get rid of this. You probably, you may want to do something a little more sophisticated, but basically what we're going to be doing when we actually modify the code for this week is we're going to be reading one character at a time, and we're going to be looking for to see if the character we just read is part of one of two sequences of characters. Now, the two sequences of characters are ON for on and OFF for off, and so when somebody types one of those two sequences of characters, and as soon as we recognize the full sequence, we're going to issue a change to the state. Now, technically, it's a change to the state, even if because we're issuing a change, a write to the LED. Even if you type the same sequence multiple times in a row, you type off, 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 we're always going to send in a write to the LED 0, turning it off, even though it's already off, or on. We're gonna, if you type in on several times in a row, it'll just stay on, but we'll be issuing a state change right each time we recognize that sequence. We don't care if it's already on, we're still going to turn it on. So technically, every time you read a character that completes one of those two sequences of characters, we're going to have some logic that tells us what the state is based on that, which of those two sequences of characters you typed in, and we're going to issue a write sending that state into the LED 0. So that's what I came up with for a finite state machine diagram. So we've got two states on, LED off. And this is how we determine which of those two states we're in. It's going to initially be off. And then as you type in a character, we're going to keep track of the fact that you've entered a sequence, and that you're still in the sequence. In the case of off, with on, it's much simpler. You don't have anything in the middle here. You begin the sequence, and then the very next character ends it if that character is n. In the case of off, if the first character is uppercase 0, we know that we're beginning one of those two sequences, and so we increment a sequence index variable from 0 to 1. So the sequence index is 1 after we read the 0. So then the next character we read, if the sequence index is 1 and the character we've just read is F, then we simply increment the sequence index again, and then the third character we read, if sequence index is 2, and the only way the sequence index could be 2 is if we have just read a 0 and an F. I'm sorry, not a 0, an O and an F. And then the third character, if the sequence index is 2 and the third character we read is also an F, then we've completed the sequence. We know that the state is now supposed to be off, and so we issue a 0 to LED 0. So that's it. That's your finite state machine diagram. You don't have to do it exactly like I did. Probably not a good idea if you do, but just be creative, do something that makes sense to you. But this is the tool, app.diagrams.net, and then start with a blank diagram and just start dragging on some controls here. You may want to go with the UML items here. But you know, I couldn't find anything like this, for example, in UML, so I went up here to advanced, and I found something that looked like what I wanted. So just have some fun with this. But I just wanted to show you that because that sort of took me by surprise. I was reading through all of the things you had to submit, and I wasn't expecting that one. And I'm sure you probably wouldn't be either. But here it is. It's not so bad. So that's your one of your deliverables. And then export it to PDF. So to do that, it's just file. So first, file, save, or save as. Put it someplace on your local machine, or you want to save it. And then do a file, export as PDF. And you'll probably want to do a fit. First, I did a page view, and it was all cut off. Part of it was on one page, part on another. I would just do a fit, one sheet across, one sheet down, depending on how big you make your drawing, but I would think one page should do it. It's a fairly simple state machine, and then just export it. And I believe on my machine, when I exported it, of course, it went into the downloads folder. So I'd go there and look for it, and then copy it someplace you want to save it. So that's that. Now let's take a look at your assignment, your coding assignment. Okay, now we're going to go here, milestone 2, UART GPIO lab guide. So let me mention first that you probably have a newer version of the SDK than they're assuming you have here. I believe this is written for, let's see. Yes, Simple Leak CC32XX SDK 4.30.00.6. This set of instructions is written on the assumption that that's what you have. Well, you probably have a newer one. I have CC32XX SDK 7.10.00.13. So if you go looking through the Resource Explorer for UART Echo in using the paths that they take you down, you're not going to find it. So I'm going to show you how to find it. Okay, so let's open up the Resource Explorer. And we want to go to wireless connectivity, embedded software, and look for this one. This Simple Leak SDK 7.10.00.13. You see it has this green check mark beside it. That's the one you've installed. Assuming, of course, everyone has been keeping up, and we're in Module 3 now, so you should already have this installed locally. This SDK. So under there, we're going to look at examples and then find your board. I have the CC3220S Launchpad. Some of you may have the SF. Whichever one you have, pick that one. So I'm going to pick the S. And then we're going to look under TI drivers and look down here for UART2 Echo. Now that's one of the major differences in the old SDK that they assume you have. SDK4, and I have 7, and hopefully you all have that. If you do have the old one, the instructions provided in the module should be great for you. But if not, then you'll have to look at what I'm doing. And but anyway, what I was going to say is one of the major differences in those two SDKs in the old SDK4, they were just using UART, not UART2. Now, UART2, as I understand it, has some asynchronous capabilities, some callbacks, so that it's not non-blocking, and you can send stuff off and then go and do something else, and then when that finishes what you started before you went off to do something else, it'll go to a callback routine, and so you don't have to wait for it to come back. So anyway, but now we're using UART2, so it's not UART echo that you're looking for, it's UART2 echo. And we want to go no RTOS. And by the way, this is an important thing too. In the instructions you have, it tells you to use the I believe it's the CCS compiler. That I believe has been replaced by the TI CLang compiler. So go there. Unless you have the old SDK, if you have something old and you see the CCS compiler under here, I'd go ahead and use it. But if you don't, then the one you want is the TI CLang compiler. And so then click here and import this to the CCS, the Code Composer Studio IDE. And of course, I've already done that, so I'm not going to do that again. But that's what you need to do to get started. But anyway, that's the path to it. It's totally different than what those instructions you're looking at show you. So let me close this. Now, the first thing you need to do once you get it over here is build it and load it onto your board. You should be familiar with that already from modules 1 and 2. So I'm not gonna, I may have to load it here in a minute, but I'm not gonna go through all that, because if you need to see that, I believe I covered it in the modules 1 and 2 videos, and you could go back and look at that. But the first thing you need to do after you load it onto your board is just familiarize yourself with the baseline behavior of the UART2 echo program, and really all it does is now your code here is going to look much different than actually that's the code that I wrote for the state machine. We're going to get into that later. I've commented out this code, but if you've found this, you're looking at the code. But it's just going to loop forever, reading characters that you type in and echoing them back out to you. That's what it does. It reads in what you type and puts it back out for you to see. So what we want to do, but go ahead and run that and type in some characters in the terminal. And oh, by the way, speaking of the terminal, um, let's see. I'm working on a MacBook Pro, so I don't have the COM ports, COM1, COM2, that sort of thing to pick from. So um, I've just been picking one of these USB modem ports here, and so I'm working with this one, USB modem E008101001. That's, of course, peculiar to my machine. It'll be different for everyone. But if you're working on Windows, the instructions about how to find the port that your board is assigned to via the USB port, those instructions are pretty clear. If you are working on a Mac and you have some issues and you can't find it on Google, just get in touch with me and I can help you. So anyway, I've got this code here that I wrote. So remember what I showed you in the state machine diagram. We're just going to be listening. We're still in an eternal loop here, listening for key stroke inputs. We're going to read one character at a time, and we're going to write it back out immediately. We're going to echo it back out. And then we're going to apply some logic here. Now I've got a holder here, a character input holder that I defined up here, and it's a car. The type is car, so it's only and in the instructions. Let me see. Let's take a quick look at those instructions for what you need to do. Here it is. So after working through this process, the process being getting familiar with, you build and load the program onto your board and then run it and debug and type in some characters and see that it echoes them back out. So once you're through with characterizing the baseline behavior for yourselves, this is what you need to do. Oh no, those are the questions, excuse me. This is what you need to do. Use only 1 byte of RAM for the serial buffer car input. And so I accomplished that by defining my buffer, the variable that I'm going to read into as a car type, data type of car, which is 8 bits, 1 byte, and so that takes care of that. Use only 1 byte of RAM for the state, unsigned car state. Receive only 1 character at a time. It's not buffered, so in other words, as soon as you type it in, we're going to spit it back out, and then we're going to use that character we just read to start reasoning with it and seeing if we're in part of the sequence. So let's go back here then, and here's our unsigned car state, and then we have a command index. So what we're going to do is command index starts out as 0. And so every time we read a character, we're going to check see what the character is. If the character is O, uppercase O, and I just made it case sensitive. You could, if you wanted, I don't recommend spending the time making it case insensitive, but that's up to you. So this is case sensitive. It's looking specifically for uppercase O. Okay, if that's the character you just typed in, then we're going to check, we're going to set command index to 1. We don't really need to check to see what it was before, because we know that that's the first character in either of those two sequences, ON or OFF. So we're going to set the command index to 1. Okay, else so let's say command index is already 1. So if command index is 1 and the character we just input is uppercase N, then we've already arrived at a state decision. State is going to equal 1, and then we're going to write that to the LED 0, and we're going to use this constant. It's a 1, but you can just hard code in a 1 there. It's not a best practice, but we're just doing proof of concept right now. So, but it's always good to stick with the best practices. And besides, there are already a couple of constants defined in this application, so might as well use them. Off being 0, on being 1. So we just need to pass a 1 some way or another to the LED 0. So we're going to use this general purpose input output GPIO write to do that. And then we're going to set the command index value back to 0 because we're done with that sequence. Else, if the command index is 1, and the only way it's going to be 1 is if the previous character was an uppercase O. So if command index is 1 and the character you just input is an F, uppercase F, then we're simply going to set the command index to 2, increment it to 2. Because we're sort of in the middle of a different sequence. There are only 2 relevant sequences of characters we're looking for, ON and OFF. So we know that if it was 1, then the previous character was an O, and if the previous character was O and the current character is F, then we simply increment the command index to 2. And then else if command index is 2 and the current character is an F, then we know that we just had an uppercase O followed by an uppercase F, and now we've got another F, so we're done. We've arrived at a state decision. State is 0 for off, and we're going to write 0 to LED 0, and then we're going to again set the command index back to 0, because then we're watching for another command sequence. Else, so in other words, if none of these other things are true, so we haven't typed in an O and an N or an F or a couple of Fs, then we simply set the command index back to 0, because whatever character they've typed in or that you've typed in is not part of one of the two consequential relevant sequences. It's an inconsequential sequence. So we reset the command index and keep listening. So that's it. That's the state machine. So let's see what we can do now. I'm going to disconnect my board. Now I'm going to connect it again. And as you can see, it's still running last week's program. It's got the going back and forth between 10% and 90% and 0 and 90% for the two LEDs. So now I'm going to load the UART2 Echo, the modified UART2 Echo on here that has our state machine in it. Okay, so now, as you can see, remember we started it out as off. It says ensure LED starts in the ensure the LED starts in the off state, and so that's why you don't see LED 0 at all. You just see LED 1. So let's debug. And run it. Now where is my terminal? Terminal, and it's already set up here for it looks like to listen on the correct serial port, but if it were not, you would just click this little open a terminal here and select the right COM port, and you want this baud rate at 115/200, data size 8 bits, parity none, stop bits 1, and I would just stick with this default encoding. So it's still retaining what I was typing in before here. So let's see, I'm going to type in on, put the caps lock on. And let's see. Okay, it finally started working, letting me type in there. So as you can see, LED 0 is now on because I just typed in on. Now I'm going to type in off, O-F-F. Now it's off, O-N, you see there's no buffer, so I don't have, it's not going to wait for me to type, to hit enter or anything like that. As soon as it reads the final character in a sequence that it's looking for, then it's going to make that state change. And I'm gonna type enough so that it gets out here past what we had typed before. So now should be able to, it should be more clear what I'm doing. O-N O-F-F O-N O. No, I typed a P, so that didn't do anything. So, but all I got to do is correct type an O. Off. So that's it. A lot of fun, really. That's the coding assignment. So let's go back and take a look at your deliverables again. Need to create a state machine. Anyway, remember to make a little video showing, 10 seconds, showing your LED 0 going from on to off based on your keyboard input. And if all I see is the board and the LEDs, but I have your code, I'll know that you were doing that. So don't worry about making anything fancy so that I can see you typing and the board. I'll know. So again, what to submit. Once you've completed this lab, zip up your workspace and submit the zipped file. Second, submit a 10-second video of the LEDs blinking on your board. And as it says, reach out to me if you have any issues with that. Now, if you're, excuse me, if you're not able to get your state machine working just right, when it's time next Sunday to submit, just go ahead and submit what you've got, and we'll get together via email or discussion board or on Teams some way, and we'll get it fixed. So I want everybody to get full credit for everything. Third, submit a document containing your answers to the questions in the lab guide. Now, I didn't talk about those questions in this video because there's a lot of stuff to cover, but I will address them in the announcement that always accompanies these videos. So, and you're welcome to Module 3 announcement. Look for something about those questions. Finally, your state machine diagram. Don't forget that. And always take a look at the rubric for any assignment, even a discussion board. There's always a rubric, and I'm required to evaluate all submissions by the rubric. So, in other words, I have to pick something for each section of the rubric. In addition to making my comments and feedback, I have to pick in other words, if I don't see anything in your submission that addresses that section of the rubric, um, I have no alternative but to select not evident, and then you lose all those points. And I really hate to do that because I want everybody to make an A. I want to help you do that. So if you do, however, miss something and you see you missed a bunch of points, you're always welcome right up until the very last day of the term, just as long as I see it before the final grades are due and in time to actually reevaluate it. I will get you those extra points. And so just be aware of that, and please take advantage of that, because it could be weeks later after you've missed an assignment or missed a few points on an assignment. You're always welcome to correct that right up until it's it's all over. Once the term's over, of course. Now, if you've done 70% of your work, and we come down to the end of the term, and for some reason or other you weren't able to get everything done, if you've done 70% of the work, you can always do an extension, and you can get the work to me a little bit later. And I'll just give you an incomplete, and then you would get a better grade than if you just went ahead and finished up the semester with only 70% of your work done. So keep that in mind too if some emergency comes up. Anyway, that's what I wanted to show you, and I apologize for I'm rambling. It's late at night, so just wanted to make sure I covered everything that I intended to. And have a good week, and let me know if you need anything, and I'll see you next week.